Good morning, everybody. Welcome to this first meeting or first lecture of game theory and optimization. Before we start with the lecture, or at least part of the lecture, let me first introduce myself. My name is Dries van Meulen, and I will be the lecturer for the first 3 weeks of this course, namely the part that concerns the game theory. In the first week, we will mainly talk about Bayesian games and their applications. So what I'm going to do is to record 4 short lectures. And the first one, this one, I will introduce the notion of Bayesian games and the solution concept of Bayesian Nash equilibrium. And in the remaining 3 lectures, I will give that hands and feet and show you how you can use these notions in applications. So let's go to the lecture slides. Got the slides here. Let me put them in full screen mode. That's a bit more convenient. So here we are. The slides I will present like this, and I'll simply comment on the slides and guide you through all the notions. So the outline is over here. That's what I already said. So we are going to have 4 lectures. The first one being this one, in which I will talk about the Bayesian games and Bayesian Nash equilibrium. And then the applications are 3. First one is signaling games. The second one, auction design and auctions. And the third application is IDDS, that stands for iterated deletion of dominated strategies. And you could say that is in a type of solution or technique to solve certain Bayesian games. Not all of them. You need to have a very specific setting for this technique to work. But you'll see how that looks like. And the other 2 applications, signaling games and auction design, are simply, you could say, types of Bayesian games that are used quite a lot in economic contexts. Okay, but let's start at the beginning, which is the definition of a Bayesian game. The definition is basically here. A Bayesian game is a collection of items or of notions or space specified over here. You've got the N, the AI, the TI, the EIs, and the UIs. And so these 5 ingredients constitute a Bayesian game. And I will just step by step explain each of these ingredients. The first one being the capital N, and that is, if you have seen game theory before, usually the set of players. So it's a finite set, 1, 2, 3, 4, up to N. And these are the players in the game. In applications, they're often called something else than players. Usually they're called bidders or buyers or sellers or agents in economic applications. So that's all the same, but from a game theory perspective, these individuals in the setting are called players. That's usually what the terminology that we will use. The next ingredient, the AI, those are the actions that player I can take. And so the index over here is an I in N, and each I in N has a set AI of possible actions. And yeah, like it's stated over here, those are the possible choices that the player can take in the game. The next one is TI, the types. Each player has a set of possible types. And types represent, you could say, the uncertainty that players are facing. So, for example, you may not know exactly the payoff function of your opponents, of the other players, if you're one of the players in the game. And that uncertainty is then modeled by different types of you. So if you have a certain type, then you think that your players will have such and such and such payoff functions. So that means that knowing your type represents information. The more you know about the types, the better informed you are. That's how you should read this. If you don't know types, then you have uncertainty because you don't know exactly which game you're facing. So that is the representation of information, or lack of information, you could say. We'll give that hands and feet in the application, so then you'll see how all this works. But for the moment, this is just the set of types. The next ingredient is a utility function. Each player has a utility function or a payoff function, if you wish, if you use more game theory terminology instead of economic terminology. And so a payoff function has as input a and t and an a, and maybe that needs a bit of explanation. So the t over here is called a type profile. It means that for each player, 1, 2, up to n, a type is given. So we assume here that ti is now the type of player I. And in the same way, the a is a vector. A1, A2, up to AN. Maybe we should write that Ti is an element of this set, capital Ti. And each AI is an action of player I, so that he could take. And so you have a vector of types and a vector of actions, meaning that the type for each player is given, and the action that that each player is taking is given. And once that is all known, each player gets a payoff, and that is then denoted by the UI of TA. By the way, these vectors over here, so this is a vector, of course, of length n. But in game theory and economic lingo, this is often called a profile. So this is a type profile, the T, and the A is an action profile, a profile of actions. Okay. So I hope this is now clear. The UI is the utility function, and its inputs has a profile of types and a profile of actions. And the last ingredient, the one I skipped over here, is the PI, and those are the priors. So each player has a prior probability distribution, and it is a probability distribution on sets of types. So you could so PI is a probability distribution on what is denoted by T minus I, which is the product space over all types. Other than yourself, you could add the prior even over all profiles, but typically you know your own type, and so you have a probability distribution over realizations of types for players other than yourself. So profiles of types other for players other than yourself. So TI is skipped, and you have a vector of types for the other ones, and each such realization has a certain probability according to player I, and all those probabilities are recorded in PI. In general, you could, if you really look at it ex ante, you can have the PI on this set, so on the complete T, so even before you know your own type. And yeah, so like I said, it yeah, so here it's on all the type profiles, so not only on T minus I, but on T. So there's a probability that this profile is realized, like I said, or at least that player I thinks that it's realized. But usually all these PIs are the same. So that means that we all assign the same probabilities to realizations, meaning that there is, in some sense, a true objective probability that this will happen. And that's, of course, the usual setting in which this is being used. So you can usually think of the PIs as just one probability distribution over capital P for all the players. Okay, so how these are the ingredients of the game. So now, how is the game played? Well, it works as follows. First, we have this prior, the P that assigns probabilities to type profiles. And the first thing that happens is that we make a draw from this probability distribution. So we randomly draw a profile of types according to the prior, the probabilities that are specified by the prior. Then, once this draw is made, these types are privately communicated to the players, meaning that each player gets to hear his own type. You see there's a typo over here, I'll correct that. So each player gets to hear the realized TI, and that means that you only know your own type and you have no information about the types of other players. So that is exactly how asymmetric information is modeled in this game. So Bayesian game is a way to formally model that kind of information structure. Okay. And now what are you supposed to do being a player? If you're player I and your type is TI, then you know your own type, not the types of the other ones. And then given that information, you need to select an action from your set of possible actions, capital AI. And once everybody has done that, so all the players simultaneously make such a choice. And once that is done, we have a vector T of types that is realized, and we have a vector A of all the actions that are chosen. And so this is the profile of actions that is then realized. And then we have a T and an A, and everybody gets a payoff. So every player I gets a payoff UI of TA. And then the game ends. This is the game, and yeah, in this for such games we have an equilibrium notion in which so you know what the Nash equilibrium is. It means that given so it's a profile of strategies with the property that if given what the other players are doing, your action maximizes your expected payoff, and you can also introduce a notion like that in this context, and that is Bayesian Nash equilibrium. So it's a Nash equilibrium for Bayesian games. And it's defined as follows. we are going to look at mixed strategies, meaning that you do not only select AIs given your type, but if you know your type, you can also choose actions with a certain probability. And set of all probability distributions over this finite set AI is denoted by delta AI. And what's now a mixed strategy? A mixed strategy is a function Si that assigns to each possible type for player I such a mixed strategy or mixed action. Why do we do that? Well, because we want to have an ex ante notion, meaning that you don't know exactly what other players will, which type will be realized. So you need to have for each possible type, and for each type that is possible, you need to know what that type will do. Otherwise, you cannot compute expected payoffs. So it's an, you could say, in that sense, an ex ante notion. So for each realization Ti, it selects an action Si of Ti, and that is then the probability distribution over all actions. So like I said, it's an ex ante plan of action. So before you even know your type, you have to say, if this and this would be my type, then I will play such and such strategy or action. That's what it says here. For each eventuality and for each possible type that might be realized for you, you have to select the corresponding mixed action that you will then play if the type is realized. Okay, so now we have for each player such a strategy. Then again, you can put those in a vector, a profile. So that is then a strategy profile. And for such an object, we can state whether or not it is a Bayesian Nash equilibrium. So Bayesian Nash equilibrium is a profile of strategies with a certain specific property, namely that for every player I and for every type of that player, given the strategies of the other ones, that the chosen action in that case maximizes your expected payoff, and that expected payoff is stated over here. So this looks very impressive. So maybe it's good to explain a little bit how you read this. So what is this saying? It is a summation over type profiles of opponents. And so your type is currently Ti, and you chose action AI, and then you get a payoff, an expected payoff. And how is that computed? Well, you take a realization T minus I for your opponents, and given that T minus I, you can compute this quantity over here. What is this saying? This is saying that if this is the realized type T minus I, then you can look at an action profile. So you also say, well, player J plays AJ. And then this over here is the probability given the profile S. This over here is the probability that TJ plays a J for all J other than yourself. So the probability that the other ones, given that these are their types, indeed play this particular action. And if they do that, then this is the payoff that you receive, right? So this is a T minus I that we chose. So this is the A minus I that we chose over here. You have currently this type and you choose this action. That is what's stated over here. And then this is the payoff that you get. So that payoff is then multiplied with the probability that this is actually going to happen. And then you sum up these expressions multiplied by the probability that this type is indeed realized. So this is really literally computing the expected payoff. So the average payoff, you could say, given all the probabilities involved in all the choices and the prior. So it's quite an impressive expression. But if you think about it, this is exactly what it should be. And yeah, so this is saying that the action that you choose maximizes that particular expression. And so the choice is you choose an AI that is maximally among all the payoffs that you can realize that way. So that's what it says here. It's the expected utility given the TI and the AI. And so this means that you only put positive probability on those AIs that maximize this expression. Is this a useful notion? Well, that's what we're going to see in the next 3 recordings, where I will explain how Bayesian games and Bayesian-Nash equilibria can be used to analyze specific economic situations. And that's what we're going to do in the next lectures. So see you there.